students. This video lesson is mainly for standard level students. I'll be talking about linear momentum. I'm going to solve few examples, 3 from SOCOS and 1 past paper related with this topic. Of course, higher level students must know this topic, so please join to standard level students and listen to me. Okay, so let's start with linear momentum. Linear momentum has a symbol of P and is defined as a product of mass of the object and its velocity. Okay, velocity, not speed, it's velocity. Doesn't mean it means that linear momentum is a vector. Okay, direction is very important. The unit of linear momentum is the unit of mass multiplied by unit of velocity, so kilogram times meter per second. What does vector mean? A short example. Let's imagine an object of mass 2 kilograms which travels with speed 3 meters per second directed to the right, and the other object of the same mass which travels with exactly the same speed but in opposite direction. The momenta of these two objects are completely different. The momentum of first is equal to 6 kilograms meters per second to the right, because it's vector, so direction is important. Of second is also 6, so value is the same, but directed to the left. Okay, so direction in the case of vector is very important. Okay, second quantity related with this topic is impulse. Impulse is change of momentum. Okay, so it's a change of product of mass and velocity, which means that mass can be changed or velocity can be changed depending on the problem. Usually for standard level students the problems are related with change of velocity of the object. Remember, velocity, not speed. So simple example related with impulse or change of momentum. Let's imagine that you have a wall, okay, and an object like a ball of given mass which travels with given speed to the left towards the wall. Okay, is passed off the wall and travels in opposite direction. Let's say the speed is a little bit less because some of energy was lost due to the collision. And the question is, what is an impulse? Okay, so impulse is change of momentum. In this case, not mass but velocity changes. Okay, so what is the change of velocity? Mass is 1 and change of velocity is 9. Velocity changes from 5 to 4 in opposite direction. Opposite direction means that you have a negative sign, so you have to find the difference not between 5 and 4, but difference between 5 and negative 4, which is 9. So in this case, impulse of the ball is 9 kilograms times meter per second. Remember, very important, direction. Okay, opposite direction means negative sign. Okay, and third very important statement here is that impulse can be defined also as a product of force acting on the object at certain time multiplied by this time. This is nothing else but the second Newton's law of motion. So let's write this in the form of force, delta P over T. Force is the rate of change of momentum, okay? And this is the most general second Newton's law of motion, that force is the rate of change, how fast momentum changes. Okay, of course, in the case of constant mass and change of velocity, it can be written in standard form. Let's look. The product of mass times velocity over t. Let's assume that mass is constant. Then we have mass times change of velocity over time. And when velocity changes, the rate of change of velocity is acceleration. So we have a standard form, mass times acceleration. So force, which is the rate of change of momentum, can be written as mass times acceleration if mass is constant and doesn't change. Okay, is it clear? So let's write these three equations again. First, momentum is product of mass and velocity. Impulse is change of momentum, or it can be written as force times time, because force, second Newton's law of motion, is the rate of change of momentum. Okay, let's look. So when force acts, then momentum of the object changes. If faster momentum changes, then bigger the force. If slower momentum changes, then lower the force. So let's focus on the graph how force depends on time. So let's assume the simplest example, constant force. Okay, when constant force acts on the object in a certain time, let's name this time t and this force F, then change of momentum can be written as force times time. If force is constant and acts in a certain time, then change of momentum is the product of force and time. Of course, it can be also calculated as area under the graph. Area, that the shape is a rectangle of height of F and base of t. So base t times height F is F times t, so change of momentum. But what if force acting on the object is not constant? So let's imagine the same graph, how force depends on time. And let's imagine that you have a collision which starts here at time t1 and ends here at time of t2. And during this collision, force changes. Let's do this change as a triangle. Okay, so maximum force acting on the object during collision is F max. Of course, force varies. Between t1 and t2, we have first increasing the force, second reducing the force. In this case, impulse cannot be written as force times time, because we don't know what is the average force. Of course, if this is a triangle, you can calculate average force, but better is to use the area under the graph. Okay, so in this particular example, the change of momentum is given as half, because area of the triangle is half of base times height, times base, which is difference between t2 and t1, times height, which is F max. Is it clear? Okay, more complicated. Let's imagine that force depends on time in such way. We have something like a curve which looks like this. Okay, there is only one method how to find the impulse, or how to find the average force. You have to calculate area under the graph. Again, area under force versus time graph always represents impulse. Okay, in this particular example, you have to count squares, because usually graphs are created on graph paper. You have to count squares and multiply number of squares times area of each square. Is that clear? Okay. And last, about momentum, the law of conservation of linear momentum. Law of conservation of linear momentum says conservation, that in isolated system, total momentum is constant. Okay, which means that total momentum is constant. Which means that momentum cannot disappear in an isolated system. Momentum cannot be created in an isolated system. If in the system we have few objects, then the momentum of one object can change, but only if momentum of different object changes. Okay, so remember about this isolated system, no forces from outside world, no forces from the surroundings. Okay, let's do 3 examples and one past paper question. Okay, so let me find. Okay, maybe let's start with this example. Let me copy, paste, and read. Okay, so we have 2 bodies. Okay, one of mass 2 kilograms and other of mass 4 kilograms. Which are kept on a frictionless horizontal table with a compressed spring between them. Okay, so this is our table and 2 objects. One smaller and second heavier, bigger. Okay, there is a compressed spring between them. Okay, and this is M1 of mass of 2 kilograms, and this is M2 of mass of 4 kilograms. Okay, and the masses are released. The heavier body moves away with velocity of 3.5 meters per second. Find the velocity of the other body. Okay, so classical example of law of conservation of linear momentum. Okay, small body, small object moves in one side. The energy which was originally stored in the spring was released. Spring is not important now. Okay, and we know that M1 moves to the left. It was pushed by the spring, and with speed, let's say V1, and M2 moves to the right with speed of V2. Okay, and we know that the heavier body, so this one, travels with speed of 3.5 meters per second, in my case to the right. Okay, so how to solve this? First of all, remember that momenta are vectors. What does it mean? If there is an opposite direction, then there must be opposite sign in the case of momentum. Secondly, you have to remember about law. Okay, law of conservation of linear momentum says that momentum before this, I'm going to use before, must be equal to momentum after this, I'm going to use after. So let's start with this expression. Momentum before is equal to momentum after. Okay? Before, what is the momentum before? We have no moving objects. So if we have no motion, then we have no momentum. So momentum before decompression of the spring is equal to 0. And what is momentum after? We know that one mass travels to the left and second mass travels to the right. Let's say that all directed to the right is positive, then all directed to the left is negative. Okay? So V1 is negative. We have to add momentum of second object, M2 times V2, which is positive. Of course, you don't need to use sign here. If you will write that if you will not use sign, then your answer will be negative, which suggests that your object moves to the left if V2 is positive and represents movement to the right. Okay, so let's put data. M1 is 2, which travels with unknown velocity. I've used sign minus. Plus M2, which is 4, and travels with speed 3.5. Okay, so finally we can write that 2V1 is equal to 4 times 3.5, which gives V1 equals to 7.00 meters per second. And we know we've used minus here, which means that this is to the left. Okay, without minus, result will be negative, which suggests that it travels to the left. Okay, so this is classical example of law of conservation of linear momentum. Okay, let's do another example, a little bit more complicated, two-dimensional example. I hope I have two-dimensional example somewhere here. Yes, let's take this, 56. Okay, let me copy. Oh. Again. Copy this and paste here. Okay, we have object of mass 0.35 kilograms. Okay, which travels is approaching a moving plate with speed. A moving plate with speed 8 meters per second. The ball leaves the plate at the right angles with speed of 12 meters per second, as shown in the diagram. What impulse has been imparted to the ball? Okay, so what is the impulse? Okay, impulse is the change of momentum. Is it clear? We know that mass is 0.350 kilograms. Okay, so first of all, we have momentum before, which is directed to the left. We have ball of mass 0.350 kilograms, which moves to the left with velocity of 8 meters per second. So we can calculate momentum before, value of momentum before. as mass times velocity. So this is 0.35 times 8, which is 0.35 times 8 gives us 2.8. Standard unit kilogram meters per second. What is important? It's directed left. Okay, 0.8, 3 significant digits. We can use 2 because there is 8.0. Okay, and momentum after. After, we have the same object of mass 0.350 kilograms, but now it travels up with velocity 12 meters per second. Now we have 3 significant digits, so finally we can use 2. Okay, and the object has exactly the same mass, is 0.350 of kilograms. So we can calculate momentum after. Okay, is m times v, which is 0.35 times 12, which is 0.35 times 12, 4.2. I'm going to use 2 significant figures, 4.2 kilograms meter per second, but what is important, up. So let's look, what is change of momentum? Before, we have object moving to the left. This is our momentum before collision with the moving plate. The value is 2.8 standard units kilogram times meter per second. And finally, we have to obtain momentum 4.2 directed up. So we have to add unknown change of momentum, vector addition, to obtain final momentum directed up 4.2 standard units, kilograms times meter per second. Okay? So what is delta P? We can use Pythagoras theorem and find delta P by using 4.2 squared, the square root of 4.2 squared plus 2.8 squared. Okay? So let's solve it. 4.2 squared is 17.64 plus 2.8 squared, which is 7.84. Okay, and finally you have to add this and take square root to find final result. Remember about unit. More precise answer is also related with direction. If you know the value, then you can calculate direction by calculating this angle. For this angle we can use tangent, okay, which is 4.2 over 2.8. Use calculator and find angle, and then you have full answer including value of change of momentum and direction of change of momentum vector. Is that clear? Okay, and let's do last example related with this topic. Let's take this about loss of kinetic energy. Okay, also just a method. We have a mass 6 kilograms which moves with speed 4, collides with mass of 8 kilograms at rest on frictionless surface and sticks to it. How much kinetic energy was lost in the collision? Okay, so again, we have situation before and situation after. Yes, before we have mass traveling to the right and second stationary mass which stays at rest, and after we have these two masses connected together, traveling together. Okay, so before I'm going to use blue. We have mass of 6 kilograms which travels with speed of 4 meters per second. Standard units I'm not writing. Collides with mass of 8 kilograms, and after the collision these two masses m1 and m2 move together with unknown velocity. If you want to find how much energy is lost, first of course you have to find this velocity after the collision. So use law of conservation of linear momentum, which states that momentum before is equal to the momentum after. Okay, before we have one moving object m1 which travels with velocity v1, and after we have two objects stick together, and then these two objects move together with velocity v. So it's easy to find. 6 times 4 is equal to 6 plus 8 times v. So finally v is equal to 6 times 4 is 24, 6 plus 8 is 14, 24 over 14 is 1.714 meters per second. I use more significant figures it's needed because this is not final answer. The question is about how much kinetic energy was lost in the collision. Okay, so we have to find kinetic energy before collision and kinetic energy after collision. Okay, kinetic energy before is half of m1 v1 squared, because only this object of mass m1 moves, so only this object has a kinetic energy. So half times 6 times 4 squared is 3 times 16, which is 48 of joules. What is kinetic energy after? After collision, we have two objects moving together, so mass of these two objects is sum of m1 and m2, and these two objects move with velocity v, which was calculated. So half times m1 plus m2 times 1.714 squared gives 6 plus 8 is 14, half times 14 is 7, 1.714 squared gives 2.938, and 2.938 times 7 gives 20.56, so around 21 joules. So how much energy was lost? Difference between initial 48 and final 21, so the loss of kinetic energy is 27 of joules. Okay, classical exercise, nice, not difficult. I hope you understand this. Okay, and at the end, do one question from November 2012 session. It was quite difficult, extraordinary, so pay attention. Of course, I hope you've copied all. If you didn't copy, please copy this and stop the movie, copy this and turn the movie back. Okay, so November 2012 session, paper 2, and this is the question related with this. Okay, question B1 about momentum change. Okay, so let's look. First is state the law of conservation of linear momentum. We can omit this. In isolated system, total momentum is constant. Okay, and B. We have a gravel. Okay, gravel falls vertically onto a moving horizontal conveyor belt, and the gravel falls at constant rate 13 kilograms per second through a height of 1.9 meters. Show that the vertical speed of the gravel as it lands on the conveyor belt is about 6 meters per second. Okay, red color for this exercise. Okay, in this case we have to focus on the falling object, the gravel. Yes, so it loses gravitational potential energy and gains kinetic energy. So you can write mgh is equal half of mv squared, obtaining equation for velocity as 2gh. Substitute data, 2 times height 1.9 times g, so 9.81, 2.9.81 times height to 1.9. I'm not going to calculate this, it's around 6, so we can write that it's around 6 meters per second. I don't know what exact number is. I'm not using correct number of significant figures. You have to use calculator and calculate this. Okay, second, the gravel lands on the conveyor belt without rebouncing. Calculate the rate of change of vertical momentum of the gravel. The rate of change of vertical momentum of the gravel. Okay, so now blue color. Okay, so what is the rate of change of vertical momentum of the gravel? The rate of change of vertical momentum of the gravel is delta p over time. Okay, so delta mass over velocity over time. We know that in each second we have 13 kilograms of mass. So 13 per second, and it hits the conveyor belt with velocity of 6. So 13 times 6 divided by 1 gives 78. What is the unit? The rate of change of momentum is a force, so unit is Newton. Okay, and this is answer on the second one. Okay, copy this and let's go forward. Next, gravel first reaches the belt. Okay, let me paste it and read. Okay, gravel first reaches the belt at time equals to 0 and continues to fall. Determine the total vertical force that the gravel exerts on the conveyor belt at 5 seconds. Okay, so let's look. What is this? First of all, you have to find gravitational force. So force which gravel acts on the conveyor belt when it is placed on the conveyor belt. Okay, so what is this? This is mass times gravitational acceleration. We have to refer to time of 5 seconds. So what is a mass which falls in 5 seconds? In 5 seconds, mass is 5 times 13, because 13 kilograms of gravel falls in 1 second. So in 5 seconds is 5 times 13. And of course times 9.81, which gives, use calculator, 5 times 13 times 9.81 results in 638. 638 of newtons. Okay, but this is not final answer, because gravel acts on the belt also when it collides with the belt. We've calculated this force here in example 2. So finally we have to add this force to the gravitational force acting on the gravel. So finally, total force which acts on the belt is weight of the gravel, 638 newtons, plus 78 newtons. This is the force which is related with collision of the gravel with the conveyor belt. So the sum of 638 and 78 is 716. 716, so approximately 720 newtons. And this is the answer, okay? So total force, total vertical force that the gravel exerts on the belt in 5 seconds is 720 newtons. Copy this. Let me read next. Okay. The conveyor belt moves, paste, and here I will use red color again. Okay, the conveyor belt moves with constant horizontal speed of 1.5 meters per second. As the gravel lands on the belt, it has no horizontal speed. Calculate the rate of change of kinetic energy of the gravel due to its change in horizontal speed. Okay, the rate of change of kinetic energy is again kinetic energy, change of kinetic energy over time. Let's refer to 1 second, because we know what is the mass which falls in 1 second. So this is half of mass, 13 kilograms per 1 second, times the speed. It gains speed by 1.5, so 1.5 squared. So this is 1.5 squared, use calculator, times 13, half of 13 is 6.5, which gives 14.6 joules per second. Okay, the rate of change of kinetic energy, joules per second. So practically is 14.6 of watts. Okay, next, determine the power required to move the conveyor belt at constant speed. Oh, probably the most challenging. I'm going to use blue again. Okay, so let's look. The power required to move the belt at constant speed. In your data booklet you can find equation for power to move something with constant speed. Power is force needed to do this times speed. Okay, but what is this force? This force is horizontal force which acts on the gravel. Okay, gravel must be accelerated because at the beginning when it falls it has no horizontal speed. So we can write this as change of momentum in time times velocity. Okay, so what is a change of momentum of the gravel in time? Gravel changes velocity from 0 to 1.5 if 13 kilograms fall of gravel fall. So we can write mass in second 13 kilograms in 1 second. It changes speed by 1.5 and it must be multiplied by 1.5. So finally we have 1.5 times 1.5 times 13, which gives 29.25, so around 29. 29.25, so around 29.3 of watts. Okay, so you see difference. In previous we had 14.6 watts, now we have 29.3 watts. Okay, and finally, yeah, this is the last question in this. Okay, you have to outline why the answer in C1, so the red one, this one, okay, is different as answer in C2, this one. Okay, so let's look. In here, in red, 14.6 is the rate of change of kinetic energy of the gravel. Here is power needed to keep constant speed of conveyor belt when gravel falls on this all the time. But the difference is in the fact that this answer doesn't include the fact that gravel must be accelerated. Okay, so what is the correct answer? Okay, gravel must be accelerated from 0, this is initial horizontal velocity, to 1.5 meters per second. Okay, so there must be a friction, so conveyor belt must also produce extra force to overcome this. So finally, gravel must be accelerated, so this is the difference in the power. Okay, so I hope you understand this. Please calculate this exercise again working alone. And I'm going to make a kind of test or quick test in this week, so be prepared from linear momentum. Okay, so thank you for watching and see you on our next video lesson. Bye.